In this video, we're going to come back to the idea of limits and focus on finding limits at infinity, and then we'll see what those limits tell us about the graph of a function. So let's start by doing an example. Find the limit as x goes to infinity of 3x squared minus 4x plus 5 all over 2x squared plus 7. If I try to plug the infinity in for x, I'm going to end up with infinity divided by infinity. And that is indeterminate, just like that 0 over 0 is indeterminate. So this means we're going to have to do a little bit of algebra to try to find this limit. And so what I'm going to do is I'm going to take every single term in the numerator and every single term in the denominator, and I'm going to divide by the largest power of x that I see in the denominator. In this case, the largest power of x is that x squared. So I want to divide every single term by x squared. Technically what I'm doing is I'm multiplying the top and bottom by 1 over x squared. And since I'm doing the same thing to the top and bottom, I'm essentially multiplying by 1. So I'm not changing the value of this fraction. So I'm going to go through and divide every single term by x squared. So now I have limit as x goes to infinity, 3x squared over x squared minus 4x over x squared plus 5 over x squared all over 2x squared over x squared plus 7 over x squared. And we can do some algebra. We can simplify this. That first term in the numerator, the x squareds cancel out, and we're just going to be left with a 3. The second term in the numerator, we can cancel one of those x's out, and that's going to become minus 4 over x. And then I'll just leave that 5 over x squared. In the denominator, the x squareds cancel out in that first term. We're just left with 2, and then we still have that plus 7 over x squared. So now that I've done some algebra, I'm going to plug my infinity in. And anytime you have a finite number and you divide that by either positive or negative infinity, that is always going to go to 0. If you take something finite, so a number that's not infinity, and you divide by something that's growing without bound, the magnitude of that quotient is going to get smaller and smaller and smaller, and it's going to approach 0. So when I find this limit in the numerator, that 4 over infinity and 5 over infinity is going to go to 0. And in the denominator, the 7 over infinity will go to 0. And all I'm left with in the numerator is the 3. All I'm left with in the denominator is the 2. And so this limit is equal to 3/2. And what this limit is telling me is that as x goes to infinity, on the right side of the graph, the y values are approaching 3/2. This is a horizontal asymptote. When you are finding a limit as x goes to infinity, you are finding a horizontal asymptote. You're finding the end behavior. And you might remember from college algebra that if you have a rational function and the degree of the top and the bottom, so the exponent on the top and the bottom, if those degrees are the same, your horizontal asymptote is the ratio of the leading coefficients, so y equals 3 over 2. The calculus using limits is just a more formal way to show that, yes, that horizontal asymptote is at y equal 3/2. Now, let's take a look at a couple more examples. Let's find the limit as x goes to infinity of the square root of 4x squared plus x divided by 5x plus 2. Once again, if I try plugging that infinity in, I'm going to get infinity on the top, infinity on the bottom. So I'm going to try using the same approach for this problem. I want to divide by that largest power of x in the denominator. I have a 5x in the denominator, so I want to divide everything by x, which is equivalent to multiplying by 1 over x. So I want to multiply the top and bottom by 1 over x. Now, if x is bigger than 0, if x is positive, which it is because we're finding the limit as x goes to positive infinity. So if x is positive, the square root of x squared is equivalent to x. Square root, squared, they undo each other. Square root of x squared is equivalent to x. So in the numerator, I'm going to replace that 1 over x with a 1 over the square root of x squared. And that's going to allow me to do some algebra to the numerator. So in the numerator, technically we have a square root 4x squared plus x divided by square root of x squared. You can divide two radicals, and that is going to become the square root of 4x squared plus x divided by x squared. And then we can break this up into two separate fractions. So now I've got square root 4x squared over x squared plus x over x squared. So by writing that x as a square root of x squared, that's actually allowing me to put that x squared in the radical and do that division. Then in the numerator, we've got 5x plus 2 times 1 over x. That becomes 5x over x plus 2 over x. And now I can simplify this, just like I did with the previous problem. That 4x squared over x squared, the x squareds cancel out. We just have a 4. 1x over x squared, an x cancels out. We're left with 1 over x. In the denominator, the 5x over x becomes a 5. And then we still have that plus 2 over x. So now if I want to find my limit as x goes to infinity, I'm going to plug the infinity in. So square root 4 plus 1 over infinity, all over 5 plus 2 over infinity. And once again, anytime we have a finite number, like that 1 and that 2, anytime we have a finite number divided by infinity, that's going to go to 0. And I am left with square root of 4 divided by 5, or 2/5. So this is also giving me information about a horizontal asymptote. As x goes to infinity, the y values are approaching 2/5. Now I do want to show you what happens if I do the same problem, but I want to find the limit as x goes to negative infinity. Now whether we're approaching positive infinity or negative infinity, the strategy isn't going to change. It's just when you're dealing with these square roots, the algebra actually changes a tiny bit. But our strategy is the same. If I were to plug in the negative infinity, I still have something of the form infinity over infinity. I still want to take that largest power of x in the denominator, divide everything by that. The piece that changes is if x is negative going to negative infinity. If x is less than 0, the square root of x squared is actually negative x. It's easiest for me to explain this with numbers. So if I pick a negative number, like -3 for x, and I square that, and then take the square root, -3 squared is 9, square root of 9 is 3. Notice if we plug x equal -3 into the square root of x squared, that value changes sign. It becomes a positive 3. And that's what I'm saying at the top of the screen here when I wrote the square root of x squared equals negative x. The x value changes sign if it's negative, and you square it and square root it. All right, so what that means is if I want to replace that x with square root of x squared, to make sure I'm doing the same thing to the denominator, I really need to divide by negative x. Square root of x squared and negative x are the exact same thing. So I'm going to take my numerator, divide by square root of x squared, and I'm going to take my denominator and divide by negative x. So now I've got limit as x goes to negative infinity, square root 4x squared over x squared, plus x over x squared, and then in the denominator, 5x divided by negative x, plus 2 divided by negative x. We can still do the algebra. The x squareds are going to cancel. So I've got limit as x goes to negative infinity, square root 4 plus 1 over x, And the piece that changes is in the denominator. 5x divided by negative x is negative 5. And then I'll write the 2 over negative x as minus 2 over x. And if I plug in that negative infinity, we still have a finite number divided by something that is infinite. Doesn't matter that it's negative infinity. So 1 divided by negative infinity is going to go to 0. So finite number divided by plus or minus infinity always goes to 0. And I'm left with square root of 4 divided by negative 5, or negative 2/5. So as x goes to negative infinity, the y values are approaching negative 2/5. Now, what does this look like on the graph? These actually represent horizontal asymptotes. And what this is telling me is on the left side of the graph and the right side of the graph, we actually have different horizontal asymptotes. And so I have graphed this function, and you can see as x goes to positive infinity on the right side of the graph, the function is flattening out, and it's approaching y equal positive 2/5. On the left side of the graph, the function is flattening out as well. There's also a horizontal asymptote, but it's actually approaching y equals negative 2/5. So this is an example of a function that has two different horizontal asymptotes on the different sides of the graph. Now I want to show you a couple more examples. This idea of dividing by that largest power of x in the denominator only works if you have a fraction, because you're doing the same thing to the top and the bottom, so you're essentially multiplying by 1. I just want to show you a couple more limits where we're not going to be able to do that, and we're just going to plug the x value in and think about what we get. So let's find the limit as x goes to infinity of arctangent of x. So I plug in the infinity, and I get arctangent of infinity. And so let's actually think about what that means. This is something that we can actually reason out. What is arctan of infinity? Well, arctangent is the inverse of my tangent function. So you put a number into an arctangent function, and it's going to give you an angle. In other words, if arctangent of infinity equals some value, we don't know what it is, that's equivalent to saying tangent of something is equal to infinity. That's just the definition of that inverse function. So we are trying to find an angle whose tangent goes to infinity. And so let's think about our unit circle. Now, if we're dealing with an arctangent function, we only have to look at the right half of the unit circle. Arctangent only has outputs that go from negative pi over 2 to pi over 2. And so to help me reason this out, I'm also going to remember that tangent is the same as sine divided by cosine. So just thinking about my unit circle, for example, I remember tangent of 0 is 0 because sine of 0 is 0, cosine of 0 is 1. So 0 divided by 1 is 0. But when I get up to that 90-degree angle, or pi over 2, tangent of pi over 2 is actually undefined. And tangent of negative pi over 2 is actually undefined as well. That's because those are places where cosine is equal to 0. And so let's take a closer look at what's happening there. When you have that 90-degree angle, pi over 2, sine is positive 1, and your cosine is 0, finite number divided by 0 is going to go to infinity. When your angle is negative pi over 2, you actually have sine is negative 1. So you got negative 1 divided by 0. That's going to go to negative infinity. So when does tangent equal infinity? That would be pi over 2, when the angle is pi over 2. So arctangent of infinity goes to pi over 2. And that's going to actually be my limit. The limit as x goes to infinity of arctangent of x is pi over 2. Let's look at another example. Let's see what happens when we take the limit of 3e to the x as x goes to positive infinity, and as x goes to negative infinity. So I'm just going to plug the infinity in. As x goes to positive infinity, I get 3e to the infinity. And if I take e, which is just 2.7, and I raise it to the infinity power, that is going to increase without bound. That is going to go to infinity. So I can say this limit equals infinity. What about as x goes to negative infinity? If I plug that in, I get 3e to the negative infinity. What is that? Well, anytime we have a negative exponent, we can take that term and move it to the bottom. So I can rewrite 3e to the negative infinity as 3 divided by e to the infinity. And e to the infinity goes to infinity. 3 divided by infinity, that's my finite number, divided by infinity, that's going to go to 0. So that limit is equal to 0. And this makes sense if I remember what the graph of an exponential function looks like. I have drawn on the screen the graph of y equals 3e to the x. That's my basic exponential growth. And I can see that on the right side of the graph, as x goes to positive infinity, my y values are increasing without bound. And so that's why my limit equals infinity. But on the left side of the graph, I have a horizontal asymptote. And in fact, I have a horizontal asymptote of y equals 0. And that's what the limit as x goes to negative infinity is telling me. On the left side of the graph, the y values are approaching 0, and that is my horizontal asymptote. Let's do one more. Let's find the limit as x goes to infinity of 5 divided by x plus 3. So this one, I'm just going to plug the infinity in, and this time I get 5 divided by infinity plus 3. Well, infinity divided by 3, or plus 3, is still infinite. So 5 divided by infinity, that goes to 0. Finite number over infinity goes to 0. And so this would be an example of a function that has a horizontal asymptote of y equals 0. All right, that was my last example in this video. We're going to continue this in the next video, where we'll be putting all the information we've learned recently. So increasing, decreasing, maxes, mins, and now these asymptotes. We'll put all that information together and create graphs of functions. So as always, please let me know if you have any questions on this video.